Sir, it is visible.
Okay, great. Thanks. All right. So good morning, everyone. Sorry for the long break, but I'm feeling much better now. So I think it should be okay to resume. Okay. So just want to do a quick recap. Right. So far we have seen two optimization problems of the min cost type. So one is the shortest path problem. And the other is the minimum cost perfect matching problem. Right? And I just want to write down the ILPs for both of these and do a quick comparison. Right? So in the shortest path problem, we have a graph G. And we have two special vertices, S and T. And we have costs on the edges, which are non-negative real numbers. Okay. And in the minimum cost perfect matching problem, we have a graph G and we simply have a cost function, which is not necessarily non-negative. So it could be any real number, right? And what are the IPs that we wrote down? So let's start with the minimum cost perfect matching IP, which is easier in some sense, right? So we are trying to minimize C transpose X. C is our cost vector and X is our vector of the variables, one variable per each edge of the graph, subject to, and I'm going to write down the matrix vector notation. So in the minimum cost perfect matching problem, we want that the sum at every vertex is equal to 1, right? And the way we wrote that in the compact form is we wrote this. So this is the incidence matrix of the graph. Right? Let me actually call it the vertex edge incidence matrix. Although generally, if you say incidence matrix, that is what it means. And we also had that the vector is non-negative. And we had that X is an integral vector. So that was the ILP. And if you throw away the last condition, then you get the LP relaxation of the problem. Okay. What about the ST path problem, the shortest ST path problem? So sometimes I'll just say shortest path, but what I mean is for two distinct vertices. Okay, so here, let's go back to what we had written down in the last lecture on Friday. This is what we wrote. Right, so we are still minimizing the same thing, C transpose X. We still have non-negativity and integrality, but this one is different, right? Because it's a different problem. What we want in this case is for every ST cut, we want to make sure that we are selecting at least one edge. Okay, so so we are minimizing C transpose X subject to, let's write down the others, X at least 0 and X is an integral vector. Okay, and now instead of the vertex edge incidence matrix, we are going to have a different matrix in this case. Can someone tell me what this matrix should be? Can you read this constraint, the one which has been starred, and tell me what should your matrix be in this case? For each ST cut, we have, yeah, go ahead.
People are waiting.
Oh, sorry. I forgot to enter people. Okay, 1 second. Okay. Yeah. Thanks, Shantini. Keep telling me in case I miss anyone. So you get a notification that someone is waiting?
No, someone posted in the WhatsApp group.
Oh, I see. Right, of course. Yeah. Yeah, thanks. Okay. So I'm also going to keep a track of that. All right. Yeah. So what should the matrix be in this case? We have one constraint for each ST cut, and we want that the sum of the edges, sum of the variables corresponding to those edges should be at least one. So can someone suggest what the matrix should be? Let me give you one example so that you can see how to work on this. Supposing this is our graph that we are looking at. S is this vertex, T is this vertex. Let's say we have two more vertices, U and V. And I put some cost on the edges, let's say 2, 3, 1, 4, 5. I don't know, doesn't matter. So how many constraints will we have in this case? How many cut constraints will we have? Or how many ST cuts can you see?
Four.
4. Okay, and why is that?
So I think it is 2 power n minus 2, where n is the number of vertices.
Okay, so in this case, if you're saying 4, what would the 4 cuts correspond to? So can you give me the set Z?
So one is only S,
Only S.
one is S with U,
Okay,
and S with V, and S with U and V.
exactly, exactly.
Oh, it's only 3.
S with V and S with U and V as well,
Yeah,
right?
correct. It's 4. Correct.
So it is 4, right? Right. So if we look at these 4 sets, each of them is a set containing S, but does not contain T, and these are all the possible sets of this type, right? And it should be, in fact, 2 to the power n minus 2, because you are omitting S and T, and you're looking at all the subsets of the remaining n minus 2 vertices, right? Okay. So in particular, we want to have the ST cuts. For each ST cut, we are going to have one constraint, right? So in this case, the partial of Z0 is all the edges leaving S, so that will be SU and SV, right? So we want one constraint for this cut, we want one constraint for the next cut, and so on. Right? So what should our matrix look like? So it is like an incidence matrix, but it's not the vertex edge incidence matrix. It's a different kind of incidence matrix. What should my rows be indexed by, and what should my columns be indexed by? Right? So we are going to write down a matrix like this. We are going to put the rows corresponding to these cuts, partial of Z0, partial of Z1, partial of Z2, and partial of Z3. And we are going to have the columns indexed by the edges of the graph, right? So the edges are 1, 2, 3, 4, 5. So we have SU, SV, UV, UT, and VT. Okay. And the first cut, partial Z0, contains the edges SU and SV. So I'm going to put a 1 there. and a 0 everywhere else. If you look at the partial of Z2, that is all the edges leaving SV and going into UT, that would be, let's just write it down. So we have SU, we have VU, and we have VT, right? These are the three edges that are crossing this line I've drawn. Right? And so that's going to be a 1 here, a 1 here, and a 1 here, and the 0 in the other two places. Right? So that way you can fill out this matrix. So it is like an incidence matrix, but instead of the vertex and edges, we are going to put down the ST cuts as the rows and the edges as our columns. Okay, and in this case, we want AX to be at least 1. We want to make sure that for each ST cut, we are taking at least one edge. Okay. So this is the ST cut and edge incidence matrix. Okay, which is defined as we have done in this example. Okay, is this clear? Is the compact notation of the ILP clear? Are there any questions or concerns regarding any of this? Right, so I may have mentioned in a previous meeting that A refers to the incidence matrix of the graph. Forget that. A can refer to any matrix. Okay, so depending on the problem, you may have a different matrix A. All right, so the point I want to make about these two ILPs is that in the minimum cost perfect matching problem, we had a very nice ILP. All the solutions to the ILP correspond to perfect matchings, and all perfect matchings correspond to solutions of the ILP. Right? And the optimal solutions to the ILP, they correspond to minimum cost perfect matchings and vice versa. However, those properties do not hold in this case. Right, so let's go back to our example that I had given to you. I had given to you the following graph, and I had asked you to find the shortest ST paths by inspection. So can someone give me a shortest ST path in this example? What do you think is the shortest path here?
I mean, one could be S, V2, V4,
Okay.
VT, and T.
Okay, that in fact is a correct one. S to V2 to V4 to V6
to
to
T.
T, right? And the cost of this is?
5.
5. Okay. So the cost
But
of this
then
path. Yeah.
you have a lot of ST parts, shortest ST.
Are there a
S2,
lot of them?
yeah, S2, V2, from
Yeah.
V2 to V3 to V4, then again V6 and T.
Yes, that would be another. So instead of going from V2 to V4, you could take a detour through V3.
And another is S2, V5 to V6
Yeah.
to T.
Right, that's also correct. Yes. So there are at least 3 shortest ST paths that you pointed out. Yeah, good. So in fact, those are the shortest ones. I was checking when I was making this example that you can't get a path with cost 4. So okay, so this one will do. Let's look at the one you first mentioned. So S to V2 to V4 to V6 to T, right? So this is an optimal, this is a minimum cost shortest path, right? Sorry, this is the shortest path, right? But by shortest, we mean the minimum cost. Okay. So this will give us a solution to the ILP, which would be to set all of these edges to be 1. So all the x variables for these edges, you would set to 1, and the others you would set to 0, right? And this will give you an optimal solution to your ILP, right? But you can also include some other edges in your optimal solution. For example, this edge has cost 0. Instead of putting the 1 over here, you could increase the variable to 2. So you can put x v4 v6 to be equal to 2, and that would still have the same cost. Right? And another thing you could do is you could add other edges of 0 cost. You could turn this edge, the variable corresponding to this edge, you can put it equal to 1, for example. Right? So you have other optimal solutions that don't quite correspond to shortest paths, but they do contain shortest paths. In particular, if you look at all the edges that have a non-zero entry in your solution, those edges will contain a shortest path because of the proposition we proved last time, which was this one. If you take any subset of the edges that meets every ST cut, then that subset of the edges will definitely contain an ST path. Right? So the point I want to make is that in this ILP, every solution to the ILP contains an ST path. Right? So if you look at the non-zero edges as per your solution, those will have an ST path in them. And every optimal solution contains a shortest ST path. In fact, if you assume that your costs are strictly positive, then the optimal solutions will be exactly the shortest ST paths, right? Because then you won't be able to take the 0 cost edges more number of times because there are no 0 cost edges. In fact, if the costs are positive, then all optimal solutions to the ILP correspond to shortest paths of the graph G, shortest ST paths, and vice versa. Okay. We want to make the assumption that the costs are positive because everything we are going to do also works for 0 costs. It does not work for negative costs. That is something I would like you to think about. In particular, this ILP, if you allow the costs to be negative, it would not actually capture the problem correctly. Does anybody see this? Supposing I have an edge with a negative cost. What's the problem then with this ILP? Does it have an optimal solution? Supposing I allow some edge cost to be negative, right? Which we are not allowing in general, but just for the sake of argument, let's say we allow the edge cost to be negative. Then what is the problem with this integer linear program? Supposing in this example, I allow this edge to have -2 cost.
I mean, we'll always get a set. I think that edge will be always included in the set. The optimal
Right.
solution.
Right.
But
It will
then-
be included, yes.
But I don't think it's a problem, right? I mean, we'll always have a ST path, right?
We will have an ST path, but the ILP, does it have an optimal solution? So you're right, this edge will always be included, but can you say something stronger? By included, you mean that the X variable for this edge would always be set to at least 1, right?
Yeah.
Right. So I set it to 1. But now can I not increase it?
Okay, I see.
Right. So in fact, you won't have an optimal solution at all because you can keep increasing the weight of this edge in your solution. Right. So that is one reason to not allow negative costs. And in general, the primary dual algorithms that you're going to see, they don't work with the negative cost edges. Right? So that's, but anyways, even in the ILP formulation case, you see that there is a problem. This particular ILP formulation does not work for negative cost edges. Okay. Good. All right. So are there any questions or concerns regarding anything we've discussed so far?
Like, so basically in this case, we need to impose the condition that XC should be 0 or 1, but in that case, it won't be a ILP, right?
Exactly. Exactly. Right. Because when we drop the integrality condition, we want to get an LP. So that's why we are going to just put X at least 0 and integral. But because we are minimizing, except for 0 cost edges, they will actually be 0, 1. Right? So in the optimal solutions, you will actually get 0 or 1 for each edge, except for the 0 cost edges. Does it answer your question? Okay, so, all right, so there is this question, how do you convince someone that a particular ST path is actually a shortest ST path, right? We still don't know that. That a given ST path is a shortest ST path. Okay. So we can look at the cost version or we can look at the cardinality version. So you will be answering the cost version on your assignment. So now for now, I just want to focus on the cardinality version. Okay. Let's consider the cardinality case. Okay, and let me give you one example. Here is the example. Okay, so let's say this is S, V0, V1, V2, V3, V4, 5, 6, 7, 8, and 9. And this is your vertex T. Okay. So can you give me a shortest ST path in this example? So a path which uses the minimum number of edges.
S2V5 to V4 to T.
Right. So in fact, probably in this example, it might be unique. I'm not sure. But one shortest ST path is the one you gave. S to V5 to V4 to T. Okay. So now I would all like you to think about how to convince someone that this is actually a shortest ST path. And as you can imagine, it has something to do with cuts. So I'll actually give you a more concrete question. Can you give me a set of ST cuts that implies that P is a shortest ST path? So this is a path P. So can you somehow use the idea of cuts to convince someone that there can't be an ST path in this graph that is shorter than the one you have already found? Right? So the length of this path is 1, 2, and 3 edges. So you note one thing, every ST path has to meet every ST cut, right? So which means if I give you any ST cut, your ST path has to use at least one edge from that ST cut. Okay. So can you now use this observation to come up with a collection of ST cuts? I will give you a hint. It has to be 3 ST cuts. And those 3 ST cuts should prove that this is the best you can do. Right, so I'm looking for 3 sets, Z1, Z2, and Z3, so that if you look at the corresponding cuts, then somehow they imply that this is the shortest ST path in this example. Any ideas on how you would do this? Or any ideas on what properties Z1, Z2, and Z3 should satisfy? Let me give you a hint. Supposing you know that any two of these 3 ST cuts, they are disjoint. Supposing you know this property to be true, would that imply anything about the length of the shortest ST path?
So it implies that it cannot be less than 3.
Right, exactly. Okay. Why is that?
Because like every ST cut, there should be at least one edge from each cut.
Right, exactly. And the three are disjoint, they are pairwise disjoint. So you have to take one from each of them, right? Okay,
Yeah.
great. So now can you try looking for three such ST cuts that are pairwise disjoint in this example?
One can be SV0, V1, and the rest of the
Okay, so your first set is SV0, V1. Your second set is
SV5,
okay.
V0, V1, V2,
Okay.
V3, V7, V8.
Sorry, I missed it.
SV0, V1,
Okay,
V2, V3,
okay,
V5, V7, and V8.
okay. And your third cut is
Okay. All the vertices except T.
okay. So let me just put the complement of this as equal to t, right?
Yeah.
Because we know that partial of z is equal to partial of z bar, right?
Yeah.
Okay, great. Okay, so let's look at these three cuts that you have provided. So I'm going to mark them in red. So the first one is SV0V1. So which means it is very easy to view this. It is this red colored cut, right? All the three edges that are crossing this red line, they are in this cut, right? Then the green one is going to be, let's say, the second cut. So you're putting S, V0, V1, V2, V3, V5, V7, V8. Okay. So maybe is it like this?
Yes.
Okay.
Yeah.
So this is partial of Z2. Good. And this one is partial of Z1. And now the last cut that you have provided is this one. Okay, good. Exactly. So if you look at these three cuts, right? So the red cut contains three edges that are crossing the red line. The green cut also contains three edges in this example. And the blue cut also in this example contains three edges. That's a pure coincidence. That's not the point you want to focus on. What you want to focus on is that all of these cuts are pairwise disjoint. If you look at the edges in the red cut and the edges in the green cut and the edges in the blue cut, they are never the same edge. They are all different edges, right? Which means in any ST path, you have to use at least one of the red cut edges, one of the green cut edges, and one of the blue cut edges. That means you need to use at least three edges. So that gives you a lower bound on the cardinality of any ST path. And the fact that you can always find such a collection of cuts is something we'll be proving as a consequence of linear programming theory. Okay, there are also combinatorial ways of doing it, but that's not the main focus. Are there any questions or concerns regarding this discussion? Does everybody see why these three cuts prove that any ST path in this example has at least three edges? and therefore this is the shortest ST path because this has exactly 3 edges. Right. So let's just capture this observation. Let's say G is a graph and S and T are distinct vertices. Okay, so someone is waiting to join. Okay, S and T are distinct vertices. The claim is that if there exists a collection of pairwise disjoint ST cuts, let's say I call this script C. It's a collection of cuts, right? So in this example, your collection would be partial of Z1, partial of Z2, and partial of Z3. If there is a collection of pairwise disjoint ST cuts, then the cardinality of any ST path is at least the size of this collection. In fact, let me put it differently. Let me just say it differently. If script C is a collection of pairwise disjoint ST cuts and P is an ST path, then the number of edges in this ST path has to be at least as many as the cardinality of this collection, right? And what does that imply? In particular, if you see this with equality, then P is a shortest ST path. Okay? And the fact that you will always get equality is something we will be proving. So in the fact that there is always an ST path and a collection of pairwise disjoint ST cuts such that their cardinalities are equal, that is something we will be proving as a consequence of LP duality. Okay? And once you prove that, you can convince anyone that a given ST path is the shortest ST path. Right? So in particular, if such P and C always exist, by that I mean equality, then the decision problem shortest path cardinality version, you can convince anyone that a given path is a shortest path. Therefore, it belongs to NP. We will prove this in module 4. Okay, and in fact, we will actually prove something stronger for the not the cardinality version, for the cost version. And when you put all the costs equal to 1, you will get the cardinality version for free. Okay, so we will actually prove a more general statement, and you will probably get a glimpse of that on your assignment 1. Okay. All right. So this, I think, is the end of module 1. Are there any questions or concerns regarding anything we have discussed in module 1 so far? Is everybody clear with this discussion that we had here? If not, this is a good time to ask. Okay. So yeah, so here is my plan. So basically, every time I've taught a course so far at IIT Madras, I always like to do these introductions, especially because we are all in the online setting. I think it would make sense to get to know each other better. Also for those of you who have not met each other because of the pandemic, because you are encouraged to collaborate, and this might give you a way to actually find collaborators if you get to know each other a bit more. Right? We will also help you in finding collaborators more actively, but I think having introductions will already serve as some sort of icebreaker. Right? So I would like to do that. Today, I think we are close to running out of time. So I would like to dedicate the entire lecture tomorrow to introductions. So everyone will get a chance to introduce themselves, say a few things about themselves. And that's probably going to take up the entire of tomorrow's lecture. So please do attend, because I think it will help us going forward. Also, all of you in finding collaborators for assignments and just knowing each other better. Right? But as far as the content of module 1 is concerned, we are done. Just to give you a slight idea of what we are going to do further. So for the next two modules, 2 and 3, we will focus on linear programming, right? In particular, we will focus on what do the linear programs, what do their solutions look like? That is something we will start with on Monday. So we'll start with geometry, and we will be talking about the simplex method. We will actually see the simplex method in full detail, which is a method to solve linear programs. And then we will be studying a very important, probably one of the most beautiful things about linear programming, the duality theory, right? And of course, until now, we have been mostly talking about combinatorial optimization problems, integer linear programs, and the relaxations. So what we want to do is we want to look at the relaxations, which turn out to be easier to solve actually, although that may seem counterintuitive if you are seeing it for the first time. And using the theory of linear programming duality, and by looking at the relaxation, we are going to try to solve the actual combinatorial optimization problem. So finding a shortest path or finding a minimum cost perfect matching. Right? So that's going to be done in module 4. Using LP duality to solve combinatorial optimization problems. Right? And the specific method that is most popular that we'll be studying is called the primal dual method. Right? So in fact, module 4 is called the primal dual method, I think. Okay. And tomorrow's lecture, I think we will mostly be only able to talk about introductions. So I don't think we'll be recording tomorrow's lecture because you may not want it to be on YouTube, right? But we'll start recording again from Monday. But yeah, I'm here for another 10 minutes or whatever. So if you have any questions, concerns, anything you would like to discuss regarding module 1, please stay back. So maybe I'll stop recording now.